Okay, this is chapter 2.4, limits using rigorous definition. So turn to page 139. We're looking at definition 2.41. This is the definition of a limit. And it says limit as x goes to a of f of x is equal to L. And the definition says this, that for every, that's what the symbol is, for every epsilon greater than 0, there exists a delta greater than 0, okay, such that that absolute value of f of x minus L is less than epsilon, and at the same time, okay, 0 is less than absolute value of x minus a is less than some delta. Okay, that's what it means. That's what the definition says. I'm sure it's pretty clear for you. So here comes interpretation of this problem graphically. It will make sense to you in a second when I draw some pictures. Okay, let's just say we have a parabola. Okay, let's say y is equal to x squared, and let's say we have some x value too. Okay, so obviously we know the y value is 4. Okay, so when I come from the left, the y value is getting closer to 4, and when I come from the right, the y value is getting closer to 4. So we can say limit as x goes to 2 of x squared is equal to 4, because it goes the same value from both left and right, because limit as x goes to 2 from the left side of x squared is equal to 4, and limit as x goes to 2 from the right side of x squared is also equal to 4. Then we can say this is true. Well, how does this apply to the definition we have here? Okay, so let me restate that. So let me go backwards. Okay, nice things about technology is we can go backwards here. Okay, I need to keep the same graph so it will make sense to you. Okay, as far as I can go, so I can go any further. So what we're saying is this: if limit as x goes to 2 of x squared is equal to 4, what that means is this is my f of x right there, so absolute value of x squared minus, this is my L, there's my L right there, L happens to be 4, is less than some epsilon, which is a neighborhood around the 4, and at the same time, okay, absolute value of x, that's this right here, minus a. In this problem, a happens to be 2, minus 2 is less than delta. If this is satisfied, then this is going to happen. Well, what does that really mean? What does epsilon, what does delta mean? Well, epsilon is some neighborhood around 4. Okay, so you say, well, if this is true, okay, if I can pick some value, okay, in my epsilon neighborhood, okay, and if I say, and if you tell me I'm going to pick this neighborhood right here, we call that the epsilon neighborhood. Okay, go back here, I don't want to erase that. Okay, some neighborhood, we call this epsilon neighborhood. Okay, if you pick a value, okay, if you pick an epsilon neighborhood, I have to be able to find a value within some neighborhood around 2. We call that delta neighborhood. Okay, delta neighborhood. That if I take some value in delta neighborhood, plug it into my equation, my f of x value will fall within your epsilon neighborhood. So if we keep playing this game, let's say you make epsilon even smaller, okay, and then if I can find some x value that I can plug it in and fall within your neighborhood, and you keep making your neighborhood smaller, and then if I can find some value close to 2 when I plug it in, it falls inside your neighborhood. And then you keep playing this game, you say, well, what if I make epsilon really, really small, around 4? And if I can find some value close to 2 when I plug it in and I fall inside your neighborhood, if you keep making your epsilon neighborhood smaller and smaller and smaller, and I can find some values in the delta neighborhood, okay, such that when I plug it into the function, my y values fall within your neighborhood that you're picking. If you keep getting that smaller, then we can say as x goes to 2, okay, then f of x is going to go to 4. And that's what the limit means. Okay, so that's basically a definition of epsilon delta. This is epsilon is a neighborhood around L, and delta is the neighborhood around A. Okay, now let's do a problem. Okay, that is easy to work with. Let's take some even problems. Okay, we'll just make it easy on ourselves. So I'm on page 12, page 145, and this is problem number 12. Okay, in problem number 12, they say limit as x goes to -1 of 7x plus 5 is equal to -2. And then they tell you what epsilon is. They said they want epsilon to be 0.01. Okay, what they want you to do, what they want you to do is use limit definition to find the delta, the corresponding delta for this particular epsilon. What they're saying is you have this function 7x plus 5. Well, obviously it's going to be some line right here. It's going to go up like that. Okay, and then as get to -1, okay, so, or -1 right there. Okay, so let's draw it to the scale here. So if this is -1, okay, then this value is getting closer to -2. Okay, and they're picking an epsilon neighborhood of that neighborhood there happens to be 0.01. Okay, so if that's the case, then absolute value of f of x is less than minus L, has to be less than some epsilon neighborhood, and at the same time, okay, 0 is less than absolute value of x minus a is less than delta. Okay, I'm going to use this definition, plug in everything that I have. That is my f of x, so I'm going to plug it in, okay, which is 7x plus 5, okay, and my L is that value, so minus a -2, is less than my epsilon, which is that value, 0.01. And then at the same time, I have to satisfy this condition. I'm going to eliminate the 0 because that's kind of redundant for right now. So x minus a, but a happens to be that value, -1 minus 1, is less than delta. Okay, let's clean this up. This is really absolute value of x plus 1 is less than delta. So I have to make this look like that, then I can determine what my delta relationship is with the epsilon. Okay, so let's clean this up. I'm going to get 7x plus 7, absolute value that's less than, let's just make this into instead of 0.01, let's just make that 1 over 100. Okay, that's just easier to work with fractions. Then I can factor out a 7. Okay, so that'll be x plus 1 in absolute values less than 1 over 100. And when I divide by 7, I get absolute value of x plus 1 is less than 1 over 700. So I made the left side here look like that. So now I can tell what my delta has to be. For this to be true, therefore my delta has to equal to 1 over 700. So if you pick this neighborhood, which is 1 over 100 around -2, I can pick a neighborhood which is 1 over 700 around -1, and all the y values will fall within your neighborhood that you specified. Okay? Alright, let's do a couple more. So this is number 14. So this says limit as x goes to -1 of x squared minus 1 over x plus 1, okay, is equal to -2, and they tell me my epsilon is equal to 0.05. Okay, so again, I'm going to use my limit definition. Limit as x goes to a of f of x is equal to L implies absolute value of f of x minus L is less than epsilon, and at the same time absolute value of x minus a is less than delta, and both epsilon and delta, okay, is greater than 0. Okay, alright, so let's plug in everything we have. So my f of x is that, so I'm going to have x squared minus 1 over x plus 1, okay, minus my L is -2 minus 2 is less than my epsilon, which is 5 over 100, okay, and then at the same time x minus a, and that's my a right there, so minus 1, okay, is less than some delta. So I'm trying to solve for delta. I want to make this look like that. So let's clean this up a little bit. Be x plus 1 is less than delta. Okay, now let's play around with this one. So this one, top one, I can factor that. So that will be x plus 1 times x minus 1, all that over x plus 1, okay, plus 2, absolute value of that is less than, and we can reduce that, and that reduces to 1 over 25. Okay, or yeah, 1 over 20. 1 over 20. Alright, so these two will cancel out. I'm going to get x minus 1 plus 2 inside the absolute value is less than 1 over 20. Okay, and then this is absolute value of x plus 1 is less than 1 over 20. Okay, now this matches up with that, so therefore I can conclude, okay, my delta has to be 1 over 20 for all the x values to fall within that neighborhood of -2. Okay, that's for a specific epsilon and delta. So let's do one for a general case, okay, where they don't give you a specific epsilon. Okay, and let's start with, this is problem number 20. So limit as x goes to 3 of 4x minus 5 is equal to 7. Alright, we're going to prove using limit definition this is true. Okay, so here's my proof. Now my proof says the absolute value of f of x minus L has to be less than epsilon, and at the same time absolute value of x minus a has to be less than some delta. But they don't give us any epsilon in this situation, so we're just going to leave epsilon alone, just leave it as is. So there's my f of x and there's my L. Okay, so let's plug it in. 4x minus 5 minus 7, absolute value that is less than epsilon. Okay, and at the same time absolute value of x minus a, which is 3, is less than delta. Okay, let's clean this up. I have a 4x minus 12 is less than epsilon. I'm trying to make this look like that, so I can factor out a 4. Okay, Okay, that leaves me at the x minus 3 inside the absolute value. That's equal to epsilon. So when I divide by 4, I get absolute value of x minus 3 is less than epsilon over 4. Okay, and therefore I have to say my delta has to equal to epsilon over 4. So if you tell me your epsilon happens to be 1 over 10, then I can find my delta. My delta is going to be 1 over 10 over 4, which is delta is equal to 1 over 40. I found the delta neighborhood to match up with the epsilon neighborhood. So if you make your epsilon neighborhood even smaller, let's say epsilon is equal to 1 over 100, okay, then I can find the delta neighborhood, which is small, around around 3. That means all I have to do is I have to take 1 over 100, divide that by 4. My delta neighborhood is going to be 1 over 400, and then this is my new neighborhood where I can plug into the f of x, and my y values will fall within that range that you specified, 1 over 100 from the limit. Okay, and that's basically it. Okay, let's go ahead go to the next section. We're talking about continuity, which is fairly simple. Okay, so first I need to tell you the definition of continuity because this is very important. Okay, this is chapter 2.5. 2.5. I'm on page 148, and then it's a definition 2.5.1. Alright, we say a function is continuous. Well, that's kind of easy to see. So if I don't lift up my pen, then I see the curve is continuous. But if I lift up my pen, then there's a break. So continuity means break. Okay, it could be any kind of break. It could be a break like a hole in the graph, or it could be a break like you have a vertical asymptote. Okay, nevertheless, I have a break right here at 0. Okay, so I can't have break. If I have a break in the graph, then it's not continuous. Well, we have to satisfy 3 conditions to check for continuity. In the definition it says 1, f of c is defined. Okay, that means it exists. Okay, and then 2, limit as x goes to c of f of x exists. Okay, and then 3, that limit as x goes to c of f of x is the same thing as f of c. Okay, that's the definition. But what does that all mean? Well, let's take a look at that graphically. Okay, graphically it means this. Let's take a value. Okay, and let's say a curve. We have a curve that looks like that. Okay, let's call this one 5. Call this one 2. Is this function continuous at 2? No, you can clearly see there's a hole there. So there's a break. So it's not continuous. Well, which one of these? It satisfies this condition. Okay, f of c is defined because f of 2 is 5. Okay, that works. Okay, limit exists. So when I come from the left, and let's call that 3. When I come from the left, it's going to the 3. When I come from the right of 2, it's going to 3. So it's going to 3, that means limit exists. Now the question is this same as that? No, because limit as x goes to 2 of f of x in this particular problem happens to be 3. But f of 2 is actually 5. So these two things don't match up. Okay? When that happens, it's discontinuous. Okay. So let's make one where we can be continuous. So let's say, oh, let's try this one. Okay, let's take a graph that looks like this. Okay, it's closed. Okay, and then let's leave that open, because then it wouldn't be a function. Okay. Okay, let's say that's my curve right there. That's my f of x. Okay, let's call this 3. And let's call that 7 and call this one 4. Okay, so first of all, what is my f of 3? Well, f of 3 is equal to 4. Okay, so we're good to go there. We do have a value for that. It exists. Now, what about limit as x goes to 3 of f of x? Well, that's d and e. Why is it d and e? Because when I come from the left, it's going to the 4. But when I come from the right of 3, it's going to 7. Just go to two different places. So limit of this does not exist. If limit does not exist, then it's not continuous. Not continuous. Okay? So that's the definition of a continuity. So you can have all kinds of continuities. And let's go over that real quick. Okay? So when you have a hole in the graph, that is known as a removable discontinuity. When you have a vertical asymptote, that is known as a non-removable discontinuity. And then when you have a curve that goes to one place from one side and it goes to a different place on the other side, this is known as the jump discontinuity because it jumps. So this is a removable, okay, discontinuities, and this is a non-removable discontinuity, and this is a jump discontinuity. Those are the three types of discontinuities we can have. Okay, so they gave us some more definitions on page 151. So let's take care of that. So page 151. Okay, we have a theorem actually. It's not a definition. A theorem, and that theorem is 2.5.3. Okay. So if f is a polynomial and g is a polynomial, all polynomials are continuous. What are polynomials? You know, when you have like x squared plus 3x plus 1, okay, is equal to y. That's a polynomial. Okay. So there's nothing there. It's not a rational expression. It's not a fraction. So you don't have to worry about that. Okay. When f and g are polynomials, when you add them, if this is continuous and this is continuous, so therefore that the whole thing, the sum of that is going to be continuous. When you subtract two polynomials, if this is continuous and this is continuous, then when you subtract them, that will be continuous also. When you multiply two continuous functions, f times g, if this is continuous and if this is continuous, then this is going to be continuous also. The only thing you have to worry about is when you divide f divided by g, this would be continuous and this is continuous, and this is continuous only, okay, if, we'll call that if and only if, we uses 2f, if and only if g cannot equal to 0. Okay, if g is equal to 0, bottom turns into 0, this whole thing falls apart. It's not continuous. Alright, so all polynomials are continuous everywhere. Okay, let's see, do we have any more theorems? Okay, we have another theorem that is important we need to take a look at. Okay, so let's clear that. Okay, if you want to check for continuous functions in the composite functions, I'm on page 152. The homework is actually short, okay, just the theorems and definitions are long. And if you want to check and see if the function is continuous, okay, this is page 152, 2.5.5. Okay, and what it says is, in that theorem it says limit as x goes to c of g of x is equal to L, And if function f is continuous at L, then limit as x goes to c of f of g of x, okay, is equal to L f of L, okay. So if this function is continuous, when you're finding a limit of a composite function, you can go inside here to find that. You can go f of limit as x goes to c of g of x. As long as this is continuous, then you can just take this limit and plug it into f, okay, and then you'll get the answer. Okay, so let's go down to theorem, the next theorem on the same page, which is theorem 2.5.6. I'm on page 152, and this says if function g is continuous at c, the function f is continuous at g of c, then composite function is continuous at c. So if that's the problem we had, a composite function, we actually did that for the final review. Let's just make one up. Okay, let's say I have x for f of x, and let's say g of x is equal to 1 over x. Notice that is not continuous at 0. So if I go find f of g of x, which means when I take this period in there, I'm going to get 1 over x. Okay, since that's not continuous there, this one won't be continuous either. Okay, so you have to account for that. So that's why we have to, for example, on the quiz we had like f of x is equal to x and x squared, and g of x is equal to square root of x. See, that one, x has to be greater than or equal to 0. Now, this only works if f as x is greater than or equal to 0. So when you find the composite function f of g of x, okay, this is going to look like square root of x quantity squared, which is x. This one, okay, only works as long as that condition is satisfied. So this continuity of the function, original function, has to apply. Okay, and then it says this second part of the theorem says if function g is continuous everywhere, function f is continuous everywhere, g of x is continuous everywhere. Okay, so let's take a look at that. Oh, let's do one more example of this. Let's say f of x is equal to x squared, and g of x is equal to 1 over x minus 1. We know x cannot equal to 1, so this one is discontinuous at 1. Okay, so if I'm going to find f of g of x, okay, I'm going to get 1 over x minus 1, or minus 1, okay, and then I'm going to square that, which is going to give me 1 over x minus 1 quantity squared. Look, this one is still discontinuous, at x is equal to 1. Okay, alright, so let's find two functions that are continuous everywhere. So let's say f of x is equal to x to the 5th. Let's say my g of x is equal to x to the 3rd. Well, this is continuous for everything, and this is continuous for everything. So when I plug in f of g of x, okay, that's going to give me x to the 3rd to the 5th, which will give me x to the 8th, or excuse me, x to the 15th. Okay, x to the 15th. Okay, this one is going to be continuous everywhere. So as long as the original functions are continuous, okay, then the composite functions are going to be continuous for everything. Okay, now we can have continuity from the left, continuity from the right. Okay, so let's take a look at that, which is continuous on closed interval a to b. Okay, then the function has to be continuous on open interval. Okay, so let's draw a picture of a graph. Let's say we have some curve like that, and that's my a, and that's my b. Okay, so let's say it's continuous on a closed interval, and as you can see there's no breaks there, then that means this has to be continuous on the open interval too. So if you had, just look at the middle, this is on open interval a to b, okay, this is my f of x, so that means in between a and b it has to be continuous, and it is, okay, so that checks off. The second part of that theorem says f is continuous from the right at a, so when I come from the right the function has to be continuous, okay, and it is. Continuous means they're connected, okay, and that second part checks off. And then the third part says f is continuous from the left at b, so if I come from the left it's got to be continuous, all the points have to be connected all the way to the b, and then when that happens we can say f of x is continuous on closed interval a to b, including the endpoints. Okay. Then we have another theorem, intermediate value theorem. Okay, this shows up all the time, okay, on the AP test, so make sure you understand what's going on here. So I'm on page 154, okay, and it's not that hard. Okay, let's say you have some curve and they give you a picture of this curve, okay, and let's call that A, and then we're going to call this B, okay, and we'll call this function f of x, so therefore this is going to be f of b, and then this is going to be f of a. Okay, so the intermediate value theorem, okay, IVT, says if f is continuous on a closed interval, okay, and it is, and k is any number between f of a and f of b, some number we'll call that k, it could be any number, okay, and then there's at least one number x in the interval a to b such that f of x equals a. That means as long as this is continuous, okay, if k is between f of a and f of b, that means when I go over here I want to have at least one value of x that falls between a and b. Now I could have more than one value, okay, but it's going to fall between that. So how can I have more than one value? So let's draw a picture of this same thing, okay. So let's say we have something like that, okay. So that means I got that x value, and then I have that x value. So I would get two x values in between a and b. It guarantees it have at least one as long as it's continuous. And now, of course, there is a second part of the theorem. And this happens to be 2.5.8. So now let's do 2.5.9. On 2.5.9, it says if f is continuous on a closed interval, and let's draw a picture of that, and they have the picture. Okay, they have a picture something like that, and they call this A, and they call this B, okay, call this f of x, and then this is my f of A, and obviously this is my f of B. Okay, and if f of x is continuous, and if f of A and f of B, okay, change sign, meaning one is positive and the other was negative, it doesn't have to be in that order, one could be negative and then positive, that means as long as this function is continuous, it's going to have to cross the x-axis at least once. That means that's where my f of x is equal to 0. Cross more than once, but it's got to cross at least once. So if one y value is negative, the other one is positive, it's going to cross at least once. Okay, having said that, okay, let's take a look at a couple of problems which are fairly easy on page 156. Okay, number 2. It gives a graph that looks like this. You have a closed circle, an open circle, closed circle. Alright, you have to answer all these questions. We have A, B, C, D. So let's go with 2, and then they give you another value here. Okay, and then that's 1, and then this one is 3. Okay. Alright. Okay. First one. Is the function continuous on closed interval? This is A. Is the function continuous on closed interval 1 to 3? Well, between 1 and 3, no, it's not. There's a break here. So the answer is no. B. How about open interval 1 to 3? That open interval 1 to 3 means we're excluding the endpoints. Okay, that means it has to have no breaks in the middle, and this is also no. Okay, C. Okay, how about closed interval 1 to 2? Okay, well, we're including 2, but there's a break at 2, so that means this is no. Okay, D. How about open interval, not including the endpoints, 1, 2? Well, in the open interval, that means not including endpoints in between 1 and 2? Yeah, that means yes, it's continuous there. Okay, and then E. How about closed interval 2 to 3? Okay, the answer is no. Okay, because there's a open over there, so we have an open circle there. Okay, and then F. Okay, on an open interval 2 to 3, that means in between 2 and 3, and yes, it's continuous, so we say yes. Okay, so basically 14. Like I said, these are easy. So this is 14. F of x is equal to x minus 5 to the 17th power. Find the values where, if any, if it's not continuous. Is there any x value I can't use? No. So it's continuous all the time. Okay, so continuous for all x. Okay. 16. F of x is equal to x over x squared minus 1. That's my phone. You guys hear that? Alright. Is this continuous for all x values? No. I'm going to have to factor that. Take a look at that. That's x minus 1 times x plus 1. So obviously this one is discontinuous. Okay. At x is equal to plus or minus 1. Okay. Let's go to 18. Okay. So 18, I have my f of x is equal to 3x plus 1, all that over x squared plus 7x minus 2. Okay. So I have to find out, this is discontinuous where the bottom is 0. Well, I can't factor this, so I might as well go to quadratic formula and complete the squares. Let's go to quadratic formula. Okay, negative b, which is negative 7 plus or minus square root of a, 7 squared, which is 49, okay, minus 4 times a, which is 1 times negative 2, okay, all that over, okay, 4 times a, which is 1. So I'm going to get x is equal to negative 7 plus or minus square root of a, 49, okay, plus 8, all that over 4, which simplifies to negative 7 plus or minus square root of a, 57 over 4. Okay, so this function is discontinuous. F of x is discontinuous at x is equal to negative 7 plus or minus square root of a 57 over 4. Okay, alright, now one more example. I know it's a long lesson, so let's go to one more example, which is let's do number 24. Okay, number 24. Number 24, it gives a piecewise function. F of x is equal to, okay, 3 over x minus 1 when x is not equal to 1, and 3 when x is equal to 1. Okay, so find any values, if any, which function is not continuous. Well, you could look at this one and say, hey, this is not continuous at x equal 1, but remember they defined it. that when x is not equal to 1, you can use this. When x is equal to 1, okay, you have to use that. Okay, so let's take a look at the graph of this. This is really, I have a vertical asymptote at 1. Okay, so at 1, I have a vertical asymptote. Okay, so what happens to this function when I go to from the left and right? So if you look at this, so limit as x goes to 1 from the right side of 3 over x minus 1. I can't plug it in, so I'm going to plug in something close to 1 to the right of that would be 1.0001. So this becomes 3 over very small positive. So it goes to positive infinity. So that means the curve's going to shoot up. Okay. Then I got to check what happens to function when I come from the left. 3 over x minus 1. I'm putting in 0.99999. It's going to be 3 over very small negative. So that means it's going to go to negative infinity. So the curve's going to shoot down. Okay, and then what happens when I go check? Let's check the end behavior. Limit as x goes to positive infinity. So that'll be 3 over x minus 1. That's going to go to 0 because the power on the bottom is bigger. Okay, that means the curve's going to flatten out. Okay, and then what happens when I go to the left side? Limit as x goes to negative infinity, 3 over x minus 1. That's going to go to 0 also. The curve's going to flatten out. But what is actually happening when x is equal to 1? When x is equal to 1, it's going to be 3. So x is equal to 1, it's going to be 3. So look at that graph. Is it continuous? No. So it is discontinuous at x is equal to 3. Or, excuse me, x is equal to 1. Okay. Discontinuous at x is equal to 1. Not 3. Alright. So let's do one more example. I know it's a long lesson. So this is number 30, b. It's a piecewise function. Okay, and they say f of x is equal to 2x minus 3 when x is less than or equal to 2, and x squared when x is greater than 2. Okay. Alright. I got to check for continuity. We know this is continuous. That's a line. We know that's continuous. That's a parabola. So the question is, does the line and the parabola, do they come and connect together? We have to check for that, to check for continuity without graphing. Okay? So without graphing, we've got to check and see if they connect. So only place we change from a line to parabola is at 2. So first we're going to use definition of continuity. We're going to find f of 2. Well, f of 2 means this is the one that I have to use. So that's going to be 2 times 2 minus 3, which is going to give me 1. Okay. Now I can't use this one for f of 2 because it's saying this function exists when x is less than or equal to 2. Now I got to check the limit. Limit as x goes to 2 from the left side. Okay. On the left side is the line. So I have a 2x minus 3. I'm going to plug in the 2. So that's going to give me 4 minus 3, which is 1. So that means the line is going to 1 when I come from left side of 2. Then I got to go check the limit when x goes to 2 from the right side. So that means I have to use the parabola, x squared, because the parabola exists to the right of 2. So that's going to give me 2 squared, which is equal to 4. Okay, so from the left side, the line goes to 1. From the right side, the parabola goes to 4. So this one is discontinuous at x is equal to 2. And I have to show all of this work. Okay? Alrighty.